Hey everyone, Nitesh this side. Hope you are doing well. So let's start with the question. So the question is clone graph. Okay. So you have given a reference of a node in a connected undirected graph. You have to return a deep copy or a clone of the graph. Okay. So each node contain the value and the list of neighbor. Okay. So you already know like adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes the set of neighbor of a node in the graph. Okay. So we'll understand with an example. Okay, so you have given this graph and you have to make the clone of this graph. Okay, so if we clone this, we can make this graph as 2, 1, 3, 4, and we have lot of possible option. Like we can make it same as 1, 2, 4, 3. Okay, so we have various option, but we want the same graph which will look as earlier. So this is the clone of this and this is not, so this will not be a possible. So we need to make a same graph from this. Okay, so you can easily say like we can just return this graph and it will be same as, but the question is you have to make a deep copy of this graph. Okay, so first of all, and what is deep copy? Okay, so let's say you have stored three string. Let's say this is ABC, this is DEF, and let's say GHI. So these three strings are stored on some address. Okay. So this is stored on some address. Okay. This is stored on some address. Now I want you to store the same string in, like you have to create a deep copy of this. So deep copy is basically what it will do. It will create the same nodes but with different address. So this will be having A, B, C, similarly D, E, F, G, H, I. Okay. So this will be on different address. Okay. This will be on different address. So if you change anything from ABC to ABD, it will not impact this. So this is the meaning of deep copy, and the opposite of this is a shallow copy. So what shallow copy is? Shallow copy is basically it is pointing to the same value, same address. So it will point into same only. Okay. So if you change in any place, it will impact to the other place also. Okay. So let's see how we will approach this question. Okay, so let's see how we can approach this question. So this is basically a simple implementation question. Okay, so as in question it already said like this is undirected graph. So undirected graph means like it can go in any direction. So 1 is connected to 2 and 2 is also connected to 1. Similarly 2 is connected to 3, 3 is connected to 2. Or 2. Okay, so let's create the adjacency list from this graph. Okay. So adjacency list is just like you are taking one node and see with how many vertices it will connect. Okay, so for 1, you can see 1 is connecting to 2 and 4. Similarly, you can see for 2, it is connecting to 1 and 3. Now 3 is connecting to 1 and 4. Okay, so what we will do, we will start from a node. We will start from the start. We will create a new node from this and go to its children, basically to its neighbor, and update to the new node only. Okay, so what we will do, we will create a new node. Okay, so let's say we will start from here. This is our node, beginning node. Okay, so what we will do first, we will take a new node and create a new node of this value. So it will be a 1. Okay, now what we will do, we will apply DFS. Basically, we will go to its children. Okay, so for 1, you can see we have 2 and 4. We can go in any one. So let's say we go to 2. Okay, so the call goes to 2. Okay, so what 2 will do, so we will create, we will and okay, first we will do, we will find a 2. What we will do, we will go here, we will create a new node. So we create a new node. Okay, similarly 2 has again children 1 and 3. Now what we are doing is basically we will call the 1 again. So as you can see, one is already present. So we need some sort of a visited array or visited map, which can basically remove this cycling call. So what we will do, we will create a map. And what we can easily say, like one is already present. And we will store this node. Okay, so this node is stored here. So let's say this is node 1. And we will also store the second node because second node was also visited. Now, whenever the method it is visited, what we will do, we will just return that node. So we will return that node, and whenever we're returning it, we will adding it to its child. So 2 will connect to 1. Okay. Now if I throw your visited or adjacency list, it's something like this. So 1 is not connecting to anyone, but 2 is now connecting to 1. Okay, and here also I missed one part. This is 4 connecting to 1 and 3. Okay, so we are at here. So 1 we have already done. We will not go further. We will return from here. We will go to 3. Okay, so first we check whether 3 is present. No, 3 is not present. So what we will do, we will create the node and call its children. Okay, so we will create 3 and call its children. So we are at 3. We will call its children now 1. Okay, and we will also insert this 3 in our map. Okay, so we again see 1. So 1 is already, sorry, it will be 2, not 1. Okay, so because 3 is connected to 2. Okay, so we can easily see 2 is already in the map. So whenever any node is visited, what we will do, we will return from here. We will not go in more deeper DFS. We will just return from here. So whenever we return from here, we will add it to our neighbors. So in neighbor, we will add 2. So this will be a edge from here. Okay. Similarly, we will go to the further, we will go here 4. Okay, so we will check, is it present in map? No, it is not present. So what we will do, we will create a new node. We will create a new node and we will insert into the map 4 node 4. Okay, so after inserting it, what we need to do, we need to iterate its neighbors. So we will iterate this first. Okay, so as you can already see, 1 is already iterated. So we will return from here and we will insert this into our adjacency list and it will be written from here. So 4 is connected to 1. Okay, now 4 is traverse to 3. So 3 is already visited. So 3 will also return this node. So we will connect to this and we will store it. Okay, after 4 has done his work, like after 4 call is done, 4 will return back to here. Okay, so 4 will return back to here. So we will connect the edge from 3 to 4 also. So it will be 4 and 3 neighbors is also done. So 3 will come back here. Okay, so 3 come back at here. So what it will do, it will return its basically children. So 3 will return here, and as you can see, with 2 we will connect with 3. Okay, after 2's neighbor is done, we will return from here. Okay, so for 2 we have done all the processing. We will insert into the this and we will create a edge basically, but it is undirected, so it's not visible. Now we'll go further. We will come here for 4 we can see already in the map, so we will insert into the 4. So as you can see, this is a deep copy of this graph. Basically it's on other address, so we just need to do this. Okay, so let's write the code for this. Okay, so let's write the code. So what we need is, we need a map for vertices, for basically visited. So it will be of integer and a node. Map equal to new hash map. Okay, let's write the function for this. Return clone node comma map. Okay, let's write the code. Node clone not node map of teacher a node map. Okay, first step, we need to check whether this is already visited or not. So how we check? We can easily check if map dot contains key node.value. If this value is already present, we will just return the node. We don't need to do further processing. Okay. So we just return map.get this node.value. If it is not present, then we need to do some work. Okay. So first, what we need to do, we need to create a new node. Okay. So we'll create a new node equal to new node and we'll pass the current node value. Okay. After this, what we need to do is we need to mark it as a visited. Okay. So we will do map.put node.value and pass this new node. Okay. And like we have created a new node, now we need to iterate the neighbor of current node. Okay, so what we will do, we will iterate, let's give a child name to the current node, basically neighbors. Okay, so every time whenever you are iterating, you will get some node at back. Okay, so whatever node you get, you will need to insert it new node dot neighbor. So this will be my new neighbors, and I just need to add whatever you are getting from this function call. So this is a recursion call, so child. So whatever we are getting from cloning a child, we will insert into this neighbor. Okay, it's similarly like we're doing the deep copy of the previous or already created node. After that, we just return the node. Okay, let's run the code. Okay, so there is some mistake. Let's see. Okay, so we need to add map also, like in the function call. Let's run the code. So this is accepted. So we're getting the same clone of previous graph. So let's submit it. Okay, let's see. So we have missed one condition. Basically, let's say if the node is null. Okay, so if node is null, you just need to return the node. Okay, now let's submit it. Let's see whether it will submit it or not. So this is submitted, and the time complexity for this is you are doing for all vertices and edges. So it will be order of v as a vertices v plus e, and the space complexity I just taking all the vertices in a map. So this will be order of v. Okay, thank you for watching my video.